Hello, welcome to step 21 about geometric means. So this topic is actually found paired with chapter 8, all of our congruency things. But we felt that it would be better to pair it with similarity because it talks about similar triangles and the ratios and things like that. So in step 21, we will compute and apply the geometric mean of a right triangle. So let's just first talk about what the geometric mean is. So it's this ratio between two numbers where we have the mean as the denominator of one fraction and the mean of the other fraction. And these two ratios should be equal to each other. So it's a very simple equation, but we're going to kind of derive it together. So if we had this ratio, we've already been talking about how to solve ratios in step 20 when we did our similar triangles. But if we were solving this ratio, we would, or this proportion, we would cross multiply. So I would have x times x equals a times b. X times x is x squared, and then we would just have ab. When we have x squared, to get rid of that squared, we're going to take the square root of both sides. So x, or the geometric mean, is just equal to the square root of your two numbers multiplied together. Okay, so we're just going to multiply the two numbers together and take the square root. Okay, so they did one here for you. They said, all right, what if we look at 9 and 4? So they did 9 times 4, which is 36, and the square root of 36 is 6. So what happens here is if we put 4 over 6 and 6 over 9, 4 over 6 would simplify to 2/3. 6 over 9 would simplify to 2/3. And that's why this is the geometric mean, because those ratios with 6 are equal to the same thing. So let's just do one example together. Find the geometric mean between 8 and 10. So we're going to take the square root, and we're going to multiply two numbers together underneath. So the square root of 8 times 10 is 80. And then I want you to put this in your calculator, square root of 80. If it's a perfect square, then definitely write what it's equal to. You can simplify it. If it's not, let's just round it to 1 decimal, and we get about 8.9. That would be our answer. Okay, so I think that's pretty straightforward. We can do an example in class if we need to. But these geometric means, they have relationships when we talk about right triangles. So we have something called an altitude. Some of you have seen this before, some of you have not. An altitude is a segment from a vertex to the line, and it's perpendicular to the line. Okay, so this is always representing the height of the triangle. Sometimes it can be outside, like in the second example, but this always tells you your height if you are finding like the area of a triangle. So what happens is if we start with a right triangle, so this black one up here, ABC, is a right triangle. If we drop this altitude down, we will actually create two smaller right triangles, this little bitty one to the right, and then this kind of like medium size, almost the same size as the original triangle. But they're all right triangles when we drop that altitude, because the altitude is perpendicular, meaning it forms right angles. So because we have these right angles, and because of the way we've dropped the altitude down, the original triangle and the two smaller triangles that we've now created are all similar to each other. Not congruent, their angles are the same, sides proportional, but they are similar to each other. So let's go ahead and walk through this first example, okay? So what I like to do to start these, because it's kind of hard to visualize it, I like to draw each triangle the same way. So I always start by drawing the original triangle, kind of how it sits. So it's bigger. The right angle is here. And then it has that medium-sized triangle is kind of outlined in red. So I'm going to draw a medium-sized triangle in red. Or I guess this is pink, but whatever. You get the idea. But I want it to have the same orientation where the right triangle's in the same spot. The shorter leg is coming up. And then the longer side is going out to the right. And then the blue one, which is this little baby one, I'm going to draw it the same exact way. So that all these triangles, even though we're rotating them, they look the same, and it's going to help us when we actually have to write the similarity statement. So I think the first one is always the easiest. We're going to look first at the big triangle. Okay, it's sitting nicely how we drew it. We have G at the right angle. And then we have to either put F or H on this triangle. I like to think, okay, which one's the shorter side? Because in our drawing, the one running, what is that called, vertical, is definitely shorter than the one running horizontal. So F to G is definitely shorter than H to G. So I'm going to put F at the top and then H out to the side. Okay. Next, I'm going to look at the the red triangle. So this triangle here. So now my options are G, H, and J. So my first thing is, which one is the right angle? A lot of times when I do this problem for the first time with a class, they always want to say G. G is no longer a right angle because in this triangle, it's only taking this piece of G. It's not the entire angle. So this time it switches, and J is actually our right angle. Okay? Then I want you to think, from J to G, is that shorter than J to H? Or is J to H shorter than J to G? And hopefully you can tell this one's a nice, easily drawn one. J to G is definitely the shorter side. So at the top where my shorter side is, I'm going to put G, which leaves left with H for my last one. All right. Last but not least, then I'm going to look at this small triangle here. Okay, first question I want to ask myself is, where is the right angle? So we're still not looking at G because G is only this little bitty angle there, and that is not a right angle. But if we look at J, J is a right angle on this side, so it's going to be a right angle on that side. So J would be my right angle. Then my shorter side going up from J would be F. FJ is definitely shorter than JG. And then my last vertex is G. So you don't have to write these out. Once you kind of get the hang of this, you can just visually look at the triangles. But if you need to write them out, you're more than welcome to write these out every time. But now that we have them all looking the same, it's going to be a lot easier to rotate around the triangles because they all look the same. So if I went from F to G over to H, I called this first one F, G, H. I'm going to rotate the same way around the second one. That's a weird arrow. G, J, H, and F, J, to G. Okay, you could start at H and go H, F, G, that's fine. Just make sure you start and rotate the same way around each of the triangles. Okay, but this would be our final answer. Oh, I guess I should change the size back. This would be our final answer. Okay, so continuing on with the same idea, because these triangles are similar, all their sides are proportional to each other. Okay, which then leads us back all to the geometric mean. So this is tying in the fact that we have right triangles, we have that they're similar, so we write proportions, but in the end, we're really just going to find the geometric mean between two values. Okay, so this looks like a lot, but we're going to do an example and hopefully it'll make more sense. But if we want the geometric mean of the height of the triangle, so this one we're trying to find H. We would take the geometric mean of both pieces of the base, okay? So h is equal to the square root of x times y. So we took both pieces of the base, multiplied it together, took the square root. Similar idea, if we were going to find one of the sides, we would take, so if I was finding A, I would take the side of the base that's closer to A, multiply it by the whole base, and then take the square root. Okay, so let's do an example. Hopefully this will click more as we kind of do a problem. So I'm going to turn this so that the base is actually sitting nicely on the bottom. Oh, that was not a straight line. So we have J and L and K. Okay, so this is the same figure. All I've done is I just turned it over so that we could see it nicely, that JK is going to be the base, LM is our altitude, and then we have our sides LJ and LK. So let's start with the base. So if I wanted to find X, because that's our base, I'm going to take both pieces of the base and find the geometric mean, meaning I'm going to multiply them together and then take the square root. So the pieces of the base would be JM and MK. Multiply their lengths together and take the square root. I'm doing that because I'm finding the altitude. I'm finding the height of our triangle. So when I plug in my numbers, JM is 5, MK is 20, and then I'm going to take the square root. 5 times 20 is 100. The square root of 100 is 10. So now I found X. X is 10. Okay, next I'm going to move on to Y. So if I wanted to find Y, this is a little different because it's finding the side of the triangle. So for the base, for the height, take both pieces of the base. This time, I'm going to use the piece of the base that's closer to Y. So that would be this 5 here. So I'm going to take JM, but this time I'm going to multiply it by the entire base. So if I wanted the entire base from J all the way to K, remember I would add these two pieces together. So 5 plus 20 is 25. So I take the piece closer to Y, which was 5, times the whole base, which was JK, and I take the square root. So I would do JM was 5, JK was 25, square root. 5 times 25 is 125, I believe. Oh. Okay, and then I'm going to take the square root of that. It's not a nice square root, so I'm going to just round it to one decimal place. It's about 11.2. Okay, and last but not least, if I wanted to find Z, same sort of idea. I'm going to take the piece of the base that's closer to Z. I guess I could write 11.2. So that would be 20, which would be our MK, times the whole base, which is JK, and then take the square root. So 20 times 25, square root, 20 times 25 is 500. Again, not necessarily a nice, what's it called? Square root, so it's about 22.4. Okay, and that's how we use geometric mean to find sides and heights of a right triangle. Okay, so last question. So if Zach wants to order so he's going to order a banner that's going to hang on the side of this stadium. He's using cardboard and kind of using his eye. We want to find the height of the grandstand, okay? But first we're missing this X, okay? So if we wanted to find the actual height of this, what's it called? Triangle, we could take both pieces of the base. So I could take X and multiply it by 5.75, take the square root, and that would be equal to the height of my triangle, which is 10.5. Okay, so I took both pieces of the base, took the square root, and that's equal to the height. So if I kind of rearrange this a little bit, I really have the square root of 5.75x equals 10.5. Okay, I need to get rid of this square root. So to get rid of a square root, we square something. So 10.5 squared, I would have 5.75x equals 110.25. Divide both sides by 5.75. And I get about 19.2. So if x is 19.2, to find the total height, I could do 19.2 plus 5.75, which would be about, what do we say, to the nearest foot, so about 25 feet. And that wraps up geometric mean.